Welcome to another lesson on trigonometry. Today we are going to approach the subject from a slightly different angle. We've been talking a lot about making sine tables and reading the values from it. We do this starting with geometry and using trig identities to extend what we know. These fall into the category of analytical methods, meaning there's an exact representation, something like phi equal to 1 plus square root 5 divided by 2. You can represent this exactly. Now there's also a decimal representation. If we were to punch it into a calculator like this, 1 plus 5 square root equals divided by 2 equals approximately 1.618. Now, quick side note, there's some neat features on here. Example, the memory button. If I punch that, then I wanted to clear the screen, say 1 divided by recall. This is memory recall. That'd be 1 divided by phi equals 0.618. We did a lesson about that earlier, so check it out if you want to see the details. By the way, let's do a quick poll. If you'd be interested in seeing more about these specific keystrokes you punch on a calculator, note it in the comments below and we can do a lesson on that. We did another example, sine of 58 degrees. This does not have an exact representation like this. We can only use decimal form to represent that. And here on my basic calculator, well, I could do a Taylor series which uses only algebraic operations, that is addition, subtraction, multiplication, division, and square roots. However, the Taylor series is an infinite polynomial, so it doesn't quite fall into the same category as an exact representation like this. I could use a calculator like this one that has the built-in trig functions. So by typing 58 sine, I find that this is equal to approximately 0.848048. We only have decimal representation. We don't have an exact representation like this for this angle. So in short, even if your calculator doesn't have built-in trig functions, you can use the basic operations to calculate any value of sine or cosine. If you must resort to a Taylor series, that could become quite cumbersome after a while. So now, let's push aside the analytical methods and look at it from an empirical standpoint. Empirical meaning based on measurement, observation, experimentation, if you will. What if we simply draw a diagram and measure the values to compute sine and cosine? Let's give that a try. To begin, let's assume that my chalkboard is perpendicular on the side and bottom. So that way, if I measure from the edge, doesn't really matter, I'll just say 12 inches so I have enough room to work. And I draw a line up and down. Now, same thing. From the bottom, let's say 6 inches. And I'll draw a line to connect them. Now I can pick a length. Let's say 20 inches. Measure the same on the horizontal and vertical axis. To assist me, I will use a compass. Make sure this is set to 20 inches. Looks like I have to adjust it a little bit. See if it matches up here. Get that lined up on both points. All right, trying to be as careful as possible. The more careful I am, the better my results will be. Now, I will use a protractor. And let's just mark off every 10 degrees, shall we? So line this up with my corner here. I'm just going to mark off every 10 degrees. 10, 20, 30, 40, 50, 60, 70, 80. I'll simply extend that from the corner to the arc here. Again, being careful. Okay, now there are a couple ways I can check the accuracy of my diagram here. And one simple way is to measure the arc length of each fan, and it should be the same because they're all 10-degree increments. So in my case, I'm getting about 3 inches on the first one. 3 3/8. 3 1/4. 3 1/4. Ooh, 3 3/4. Ouch. 3 1/2. 3 3/8. 3 3/8. 3 5/8. 3 3/8. So already you can see some of the pitfalls of this method. We've already lost quite a bit of precision just from the construction of this. Now, if you were more careful and using more precise instruments, this chalk, for example, has a very broad width compared to the fine line of a pen on a sheet of paper. So those are some improvements you could make to increase the accuracy of this. But now, for the sake of demonstration, let us continue with this. I will drop a perpendicular line from each intersection to the x-axis. I call this x, y. So I've dropped a perpendicular line from each point on the arc. Now, if I measure, in this case, my hypotenuse, because it follows the radius of this quarter circle, is 20 inches at each point. So the radius is constant, x over r. Remember that? Adjacent over hypotenuse. That is cosine. By placing my ruler at 0, I simply read off the measurements, and that will give me the cosine ratio at each angle. So starting at 10 degrees, I'm at 19 5/8. Then I'm at 18 1/2. This is 10 degrees, 20 degrees, 30, 40, 50, 60, 70, 80. So this is my data just by measuring these lengths here. Now, another way you can check the accuracy of your diagram is to be sure that the cosine of 10 degrees, what did we say that is? 19 5/8 should match the sine, and I'm getting 19 5/8. So that one's pretty close. What about 20 degrees? I'm getting 18 1/2 versus 18 5/8. So a slight variation there. We can do the same for 30 and 60. 17 inches versus 17 1/4. So this one's also a bit inaccurate. Lastly, 40 and 50. 15 1/8 versus 15 3/8. So that's a simple way you can check how accurate your diagram is, which will affect the accuracy of these numbers here. Now let's analyze this data.
The first 2 columns of this table are the data obtained from our measurements. The third column is simply representing the fractions as decimals. Remember that cosine is a ratio of adjacent over hypotenuse. In our case, the hypotenuse is the radius of the quarter circle, 20 inches. So each entry in the fourth column corresponds to that of the third column divided by 20. In this table, I have repeated the result of our calculation in the first column. This is then compared to the true value of cosine, obtained from the built-in function on a calculator. The absolute error is simply the difference between the first and second columns. Relative error is equal to absolute error divided by the true value. Lastly, percent error is relative error multiplied by 100. In this particular case, no measured value of cosine deviates from the true value by more than 4%. My accuracy could have been improved by using more precise instruments and being more meticulous in the process.
Another way to obtain better results is to use better instruments. In my case here, I was using inches. If I were to use centimeters, well, this goes in increments of every 5 millimeters. What if instead I had an instrument with markings every 1 millimeter? That would increase the resolution, which would give me more decimal places, assuming I drew the diagram carefully. Those are just some thoughts when you're taking the empirical approach. For many applications of trigonometry, a crude method like this might be accurate enough to suit your needs. However, let us not forget the analytical methods we've spent many hours developing. That will give us the exact answer. Thank you for watching this lesson. I'd love to hear what you have to say in the comments below. So let's discuss this. What are the advantages and disadvantages of the empirical approach versus the analytical?